Okay, so now we're going to go into how we can use derivatives to help us with real life applications. And we're going to start with understanding how it relates to what's called kinematics, which is basically the area of physics that involves motion. So like motion, like position, like speed, velocity, acceleration. Um, if you haven't taken physics, don't worry. This is why I'm trying to give you as much background as I can because I know that I have students every year that don't take physics because for whatever reason. So when they get these problems, they're very, it's hard for them to grasp at first because they never taken a physics class. So it's very important, especially if you're going to be taking the AP exam, that you have a grasp of these physics concepts because there's always a free response problem that deals with a physics application. So really take it seriously, and I'm gonna try my best to kind of make this simple, but physics tends to be a pretty tough subject. Anyways, so what we got going on here is ways to describe um, where an object is at some point in time. So we usually will have the position function of an object or whatever thing be represented as S of t. And maybe you recognize this equation from like maybe your previous math class, maybe pre-cal, maybe you saw like an example where they tossed the ball or shot a basketball, and you can recognize, wait a minute, that's a quadratic function, right? Like it makes a parabola, and you're correct, that's true. This is, if you look at this, you have a quadratic function. I'm going to get more into that in the next video, but for now, let's understand that this is an equation that will give you position of some object in general that falls under the influence of gravity. And that's because, again, sometimes I think on the AP exam they'll assume that you have to understand and know what the speed of gravity is. I don't know if they're going to make a change this year, but what this says is that the position of an object, falling under the influence of gravity, so maybe dropping off a building or something you throw in the air, is equal to 1/2 gt squared plus v naught times t plus s naught. Okay, so what does g mean first? Well, g is the speed of gravity, or more specifically, the acceleration of gravity on Earth, which in feet is about negative 32 feet per second. And we say negative because we consider moving downward a negative direction. Or if it's in meters, it's going to be about negative 9.8 meters per second squared. Now, what is about V naught? V naught is your initial velocity. So V in general will represent your velocity, and we say V naught as your starting velocity. So as soon as when t is 0, or whatever they distinguish, or whatever they say the problem will start at, this will be your initial velocity. And S naught will be your initial position, the position at the start of the problem. So let's first understand velocity, and what you're going to hear when you're doing calculus is instantaneous velocity. So like what is instantaneous velocity? What's the difference in instantaneous velocity and velocity? But let's first recognize that what we usually talk about when we're talking about velocities is technically known as average velocity. So in other words, you're really going to see average velocity or instantaneous velocity in your calculus problems. So when we say average velocity, that's simply an estimation of how fast an object is moving over some period of time, which we calculate by basically taking the rate of change equation. This is something you probably learned in algebra, where you're finding the slope of a graph. In other words, you have the change in position over the change in time. Now, for example, like what we do usually in the real world, let's say you got a buddy who's running a marathon or something, and you want to figure out like how fast is he running, like what's his speed. So you go to like mile 3. You're at mile 3. So mile 3, let's say you're standing at mile 3, and as soon as he hits the mile 3 mark, you record the time. And his time, let's call it T1, is 15 minutes. This is, again, this hypothetical example. The time is 15 minutes at mile 3. And then, you're like, okay, well, let me now see how fast he's going by recording his time later on at mile 8. At mile 8. And so then on mile 8, he's coming. And as soon as he comes by, he is at about the 33-minute mark, right? And first off, you're like, well, why would you do this? Why don't you record his speed? Well, think about it. Like, it's really hard to record speed. And it's not, you probably need some fancy equipment. And this is really not, easy to do. In other words, what's easier to do is to do this. You want to get an idea of how fast he is going by seeing how long it takes them to travel some distance. So to go from mile 3 to mile 8 means he went a distance of 5 miles, and he went a distance of 5 miles over the difference of 15 minutes and 33 minutes, over a difference of 18 minutes, which is, again, this is hypothetical, but that means he took 18 minutes to go 5 miles. So 18 over 5 means he was going 3.6 minutes per mile. Pretty fast. I assume this is probably he's probably like a cyborg. He's probably not. Like, maybe he's going downhill on he's probably on a racetrack. But again, this is a hypothetical example. But anyway, so you're like, oh wow, he's going, he's taking 3.6 minutes per mile. He's setting world records, that sort of thing. Now, let's talk. Now let's think more. What does this mean? Does this mean that he's been going exactly 3.6 minutes per mile for every second from here to here? That means he was traveling the exact same speed the whole time. And you probably can recognize, like, well, no, he sometimes maybe he's going faster than this, sometimes he's going slower. But what we mean is that on average, he was going 3.6 minutes per mile. That's his average velocity, his average speed. But we don't know exactly, we can't say for sure at what point he was going faster than that or slower than that unless we have more data. So we just say the average velocity over this time period was 3.6 minutes per mile. So that's average velocity. We're going to talk about instantaneous velocity in the next part of this lesson, but first let's go over a basic example, calculating average velocity and seeing how it relates to the difference in interval lengths. So let's say we got a billiard ball, it's dropped from a height of 100 feet, and the ball's height, which is S, at time t is given by this equation. S is equal to negative 16t squared plus 100. S is measured in feet and t is measured in seconds. And we're going to find the average velocity over each of these intervals or over each of these time periods. So first we want to figure out how fast on average it was moving from second 1 to the second second. So from time equals 1 second to time equals 2 seconds. So for this, you're basically taking S of T2 or S of 2 minus S of 1 over T2 minus T1 or over 2 minus 1. So again, this is T1, this is T2. So S of T2 minus S of T1 over T2 minus T1. And again, this is logical. You probably don't even need to really think about that formula. So we just calculate this. We calculate what S of 2 is by plugging 2 into here. And we would get a negative 16 times 4, so negative 64 plus 100. minus s of 1, which is negative 16 plus 100, which will be 84, all over 1. And what we would get is 36 minus 48. So let's go, or 36 minus 8 is 30 minus 80. We get negative 48. So we can say then that the average velocity over the first interval from time 1 second to time 2 seconds was about negative 48 feet per second. Whoops, negative 48 feet per second. Now let's look at B. What's the average velocity from t equals 1 second to t equals 1.5 seconds? So then we're basically now taking s of 1.5 minus s of 1 and dividing it over 1.5 minus 1, because now your t2 is 1.5 and your t1 is 1. So what we get is s of 1.5, s of 1.5, plugging it in, plus 100, you get 64. You get 64 minus s of 1, which we already have as 48 or 84, over 1.5 minus 1, or over just 0.5. And we get then negative 20 over 0.5, or negative 40 feet per second. So over this interval, the billiard ball was going at an average rate or an average velocity of negative 40 feet per second. And now for C, let's look what the average velocity is. Here, T1 is still 1, and T2 is 1.1. So we're going to have the average velocity over this period. It will be S of 1.1 minus S of 1 over 1.1 minus 1. Evaluate that equation for 1.1 squared times negative 16 plus 100, 80.64 minus 84. And then we divide that by 0.1. Let me actually write it out. I know. So we got S of 1.1 to be 80.64 minus 84 over 0.1. And we got negative 33.6 feet per second. Okay, so here's a basic example of average velocity. So really, again, practice with this stuff until you really understand it. And once you're good, then let's move on to instantaneous velocity, which I cover in the next video. So good luck, and I hope that helps.